When optometrists determine the strength of your glasses, it essentially comes down to the use of the thin lens equation. For example, a far-sighted eye has a near point of 100 centimeters. Reading glasses must have what lens power so that a newspaper can be read at a distance of 25 centimeters? We want to be able to place our newspaper 25 centimeters away from our eye so that our object distance is 25 centimeters. If the near point of the eye is 100 centimeters, this means that a virtual image will be formed 100 centimeters away from the eye on the same side of the lens. This is where the eye actually focuses without correction, so this is where we want our corrective lens to put the image of the newspaper when it is actually only 25 centimeters away. So we take those values into our thin lens equation and deal with all the fractions, and we end up with 3 over 100 centimeters, which is the same as 1 over 33 centimeters. So our focal length is 33 centimeters, or 0.33 meters. Now remember that an optometrist prescription specifies the power given in diopters, which is the inverse of a meter. So if we take our focal length back into that inverse, this gives us the power of our lens at a positive 3 diopters. The positive value for our power indicates that the lens we need must be a converging lens. We can do the same sort of thing with a nearsighted eye that has near and far points of 12 centimeters and 17 centimeters respectively. What lens power is needed for this person to be able to see distant objects clearly? Remember, for a distant object, we typically say that the object is at infinity. And to focus on this object at infinity, the eye must put the image at the far point of the eye, in this case 17 centimeters in front of the eye. If we assume that the eyeglasses will hold the lens 2 centimeters from the eye, then the image distance becomes negative 15 centimeters. So the focal length of the negative 15 centimeters translates into a power of negative 6.7 diopters, with a negative sign indicating that the correction will be obtained using a diverging lens. So what would be the near point in this situation? We just found the focal length at 15 centimeters, and the near point when glasses are worn is where the object is placed so that the lens forms an image, in this case 12 centimeters from the eye. Again, we are dealing with glasses, so the corrective lens will be placed approximately 2 centimeters from the eye, giving us an image distance of 10 centimeters. Since the near point is how far we need to place the object in order for the eye to focus, we want to rearrange our lens equation to find the object distance. Taking all this and using our new equation, we find the near point to be 30 centimeters. So when the person is wearing their glasses, they would need to place whatever they want to see 30 centimeters in front of the lens to be able to focus it clearly. Now what if the person wanted to use contact lenses instead of glasses as a corrective tool? In this case, the image distance would stay at negative 17 centimeters, since the corrective lens would rest directly on the eye, and we would not have to account for the extra 2 centimeters required by the glasses. From here, we can see that the power of the lens would be different than the power used in the glasses. And if we solve for the near point, we would find that it is 41 centimeters. But it's quite a bit different than the 30 centimeters for the near point for our glasses. And this really indicates that glasses give a better near point than contacts do.